So in this notebook walkthrough, we're gonna look at this notebook about linear algebra for deep learning. Um, so most of the stuff we have already touched upon in previous videos, so we're just gonna skip through them. They're not really interesting, like zero dimensional scalars, one-dimensional vectors, and all that. Yeah, these are not new stuff. We already know what they are. Um, One thing I do want to touch upon that is kind of interesting is that once we move to this part, dot products, right? Dot products. There are with NumPy, there are multiple ways of doing this. You can either call NumPy dot, or just use this operator, or you can do it this way, which is probably not recommended. But note how it uses a times b. That's the element-wise multiplication, which we'll go over in the next section. Right. So there are really three ways of doing it, and just one thing to note is the difference in operators. If you want to do dot product, use this operator. If you want to do the what do you call it, the bitwise or the element-wise multiplication, use this operator. Yeah, these two are very easily confused. Um, so another thing uh, is okay. So here we have the element-wise product, right? And use this one. I used this operator, right? And I was wondering, like, what's the point of doing element-wise product, like with dot product? It makes sense. It makes a whole lot of sense, right? If you have two vectors, dot product really gives the similarity between these two um vectors, right? It computes the projection of one vector onto the other. So that kind of makes sense, right? So imagine if the vectors represent a sentence, like if you tokenize a sentence, you get a vector representing the sentence, and you have you compute the dot product. It's really just the cosine similarity between these two sentences, right? That kind of makes sense. Now with the element-wise, or what's it called, Hadamard product. It's really like a gating operation. It only compares given two vectors, uh, how they are similar to each other per all the coordinates, on all the coordinates, right? Yeah. So that's something that we don't see a lot in like regular linear algebra, because that doesn't really make any sense geometrically. But in I guess in machine learning or deep learning, it really just computes like how two vectors, it just like process the signals, really, like a gate or something. Anyway, so then we move on to like matrix arithmetics. They're not also not very interesting, except for the fact that um, there's one connection with batching. Yeah, it's right here. It's for matrix multiplication, right? Um, Also, yes, you should be using the operator, or call matrix multiplication, right? The important thing is the inner dimension should match. But what's more important when it comes to deep learning is that you can batch processing layer. Like this thing is really powerful. It gives you this. nice feature where you can kind of accelerate processing time. So here's an example, right? Um, this will be your input, like your input is actually like 1 by 3 matrix, right? Your inputs are like three features, sorry, three parameters. So this is your one input, and this would be the weights, right? And you have the bias. Now, if you don't have the what's it called, the batch processing, and process inputs one by one, then you would do this one and multiply by this one, right? You have, sorry, hold on, 1, 2, 3. So it's really this one multiplied by that's the first column. No, it's the weight matrix is the entire thing, right? It's just the first row multiply with the weight matrix, right? And you ended up with a 1 by 2 matrix with the shape result, right? That's like one input. But if you do batch, you can process four inputs at the same time. So your input becomes a 4 by 3 matrix. And we multiply by the weight matrix and also broadcast bias, you get the output, four output points, four output samples. So this will speed up the training process like 4 times. So that's very powerful. And then we goes on to talk about some of the matrix properties. Transpose, just flips on across the diagonal, or and inverse, same thing. The more important thing is the determinant. Determinant intuitively or geometrically measures the change in value, right? If determinant, so uh you have like a set of linear transformation. Uh, if the determinant of the linear transformation is greater than one, then that means after the linear transformation, like the volume or the area of the original one gets expanded. When you have determinant equals to 0, that means on a certain dimension, it's squashed, it's flattened. You lose that dimension entirely, which means your area or your volume becomes 0. So yeah, like this one. So you have the original one like a square. So the original one is like, let's say, a 2D on a 2D plane. After transformation, the entire linear space is squashed along this direction. So imagine there's a line perpendicular to the red line. So everything is squeezed along this direction. So then the whole square becomes flattened into a line and you have 0 volume. So yeah, that's what determinant intuitively captures. Eigenvalue. Yes. So eigenvalue is also the same thing with linear transformation. The eigenvector and the eigenvalues are really just like, given a linear transformation, which direction remains unchanged. So for example, with this linear transformation, right, and the middle one, the y-axis or the perpendicular direction gets changed by this linear transformation, but the y-axis, the horizontal plane, does not get changed. It remains the same. It doesn't get rotated. It doesn't even get scaled up. So that remains the same. So you would have eigenvectors or eigenvalues equals one on that direction. So eigenvalue and eigenvectors just measures what's unchanged or what's the effect of a linear transformation. Now, why is that important or why is it relevant in deep learning? Here he explains like, okay, in PCA analysis, the eigenvectors of the covariance matrix is the principal components, uh, and the stability, right? So yeah, that's the connection. Norms and distance, very, very straightforward. We're not going into that. So you have the Euclidean distance and Manhattan distance, right? And yeah, so just like very straightforward. There you have it. That's all that we need to know with linear algebra required for deep learning. So this section is kind of the connection of how linear algebra is relevant to deep learning. That's really the activation function. Yeah, that's it. Thanks for watching.